students, I am Dr. Manisha Verma, teaching physics in Acharya Narendra Dev College, University of Delhi. I have started a lecture series on thermal physics and have dealt with various topics related to thermal physics. In my last lecture, I had started with discussions on the mean free path. What is the mean free path? On what factors does the mean free path depend? How do we derive the general expression related to the mean free path? So, taking the lecture forward and in continuation of my last lecture, today we will derive the survival equation, which is a very important integral part of the mean free path. What does the survival equation mean? It means how long or how many particles or gas molecules can travel without encountering any collision. So, we now wish to know the distribution of free paths. To do so, let us consider a molecule at the start of its journey, point O. It means we are assuming that the molecule is starting its journey at point O. We assume that the past history of the molecule is not influencing its subsequent motion in any way. This means whatever collisions that molecule may have encountered before point O will not influence its motion after point O. Suppose that a molecule moving with average speed v is travelling a distance OA, which is denoted by x, without suffering collision collision. Then, in this case, the probability of this event will be a function of x. O is x and the probability is also going to be a function of x. Let us denote this probability by Fx. The probability that this molecule makes a collision in moving from A to B will be determined by the product of the collision frequency and the time interval in which it covers the given distance. So, this figure is showing that the molecule is travelling from point O to A without colliding with another molecule. But what we add further is that this molecule is traversing a small distance AB. AB is given by dx in time dt. And let us find out the chances or the probability that this molecule is undergoing some kind of a collision in travelling this additional distance dx. We can take this to be equal to Pc dt, where Pc is the collision frequency. By standard definition of velocity, we have dx is equal to v into dt. We can then write Pc dt equal to Pc dx by v, where we have substituted dx by v instead of dt. Now, Pc by v, this will be again equal to dx by lambda. What is lambda? Lambda is the mean free path. Hence, the probability that a molecule traverses a distance dx without making a collision will be 1 minus dx by lambda. Now, motion from O to A and from A to B can be considered as two independent events. Then, the probability Fx plus dx of this molecule completing its journey from O to B without making any collision is equal to the product of probabilities for the individual events. By individual events, I mean from O to A and from A to B. Mathematically, we can express it as Fx into 1 minus dx by lambda. Hence we can write fx plus dx is equal to fx into 1 minus dx by lambda. Dx is the additional distance travelled, lambda is the mean free path, fx is the function. Now let us use the Taylor series expansion of fx plus dx and ignore the second and higher order terms in dx. Hence we can write fx plus dx as fx plus differential of fx with respect to x into dx. Then we get dfx by dx is equal to minus fx by lambda. So let us integrate it. How will we integrate it? We will take fx on the left hand side in the denominator and we will take dx, which is occurring on the left hand side, to the right hand side of the equation. Integrating, we will get fx is equal to a times exponential of minus x by lambda. Now each equation, whatever we derive, can be checked dimensionally also, whether it is dimensionally correct or not. So you can see on the right hand side, we have exponential minus x by lambda. X also has dimensions of L and lambda also has dimensions of L. So L cancels with L and we get a pure number occurring in the exponential part of the equality. So which is correct and which is desirable. Now let us derive the constant of integration a. How will we derive it? We will use the fact that f0 is equal to 1. That is, at x equal to 0, fx is equal to 1. What does this mean physically? Physically, it means that the particle is yet to move or collide. Using the relation f0 is equal to 1, we get a is equal to 1. Substituting this in the earlier derived relation, we get fx is equal to exponential of minus x by lambda. This is the law of distribution of free paths. It suggests that the probability of a molecule travelling very large distances without making a collision will be vanishingly small as is expected. This is a fact that the probability of a molecule, if it travels very large distances, it is very least probable that it is not going to encounter a collision. Now let us say we have a sample of n0 molecules to begin and only n0 exponential minus x by lambda of these n0 molecules will survive a collision in traversing a distance x. Now what is meant by surviving a collision? By surviving a collision, we mean that it traverses a distance x without undergoing a collision. It does not encounter a collision. Let this number be denoted by n to the nx. Thus we have nx is equal to n0 exponential x by lambda n. This equation is known as survival equation, and this is similar to the radioactive decay equation also. Let us plot the distribution of the free paths as a function of x by lambda. We note that the fraction of molecules with free paths larger than lambda will be given by e minus 1 equal to 0.37. Here we have plotted the graph of fx versus x by lambda. You can see that when x by lambda was 0, fx is equal to 1. When x by lambda is equal to 1, then we have exponential minus 1, which is 0.37, and the decrease is shown by the curve. So this is as far as the mean free path is concerned. Now I'll begin a very important topic in thermal physics, in kinetic theory of gases, which is called the transport phenomena. What is the transport phenomena? First of all, let me discuss this. In a gas, the velocity, temperature, or molecular concentration is not uniform throughout the gas system. Then what happens? The moving molecules will transport momentum, kinetic energy, or mass respectively from one part of the gas to another. Why does it do so? In order to achieve equilibrium throughout the gas. The gas is striving to achieve equilibrium because the gas does not have equilibrium conditions right now. It has different momentums at different parts, different energies at different parts, different number of gas molecules are occupying the position at different parts. So, by this phenomena, which is commonly known as the transport phenomena, the gas tries to achieve equilibrium in order to have a stable conditions. Now there can be three kinds of transport phenomena. The first is molecular diffusion. What is this? When the particle concentration is different at different points, then the gas will try to transport particles from one part to the other. This is called the particle transport. And because of the particle transport, the phenomena of molecular diffusion comes into being. The second phenomena that occurs in ideal gases is the thermal conductivity. The particles carry energy from the high temperature region to a lower temperature region. Due to this, the energy is transported from one part of the gas to the other part of the gas. And what phenomena originates because of energy transport? Thermal conductivity. The third phenomena is viscosity. A drag is created when particles move to a region which is moving at a different speed. So what is being transported? The momentum is being transported. And what phenomena is originating? Viscosity comes into being. This means that the transport of momentum, kinetic energy, or mass gives rise to the phenomena of viscosity, thermal conduction, and diffusion respectively. Now let us discuss each of these separately. What are we expected to learn from this lecture? We are expected to understand how viscosity comes into being. What is the mathematical formula of viscosity? What factors are the ones on which viscosity depends? So let us begin. If the different parts of the gas have different velocities, then there will be relative motion of the layers of the gas with respect to one another. In such a case, the layers moving further impart momentum to the slower moving layers to bring equilibrium state. This gives rise to the phenomena of viscosity. Now remember, the ultimate aim is to bring the equilibrium state to the gas. What happens in conduction? If the different parts of a gas have different temperatures, then the molecules of the gas will carry kinetic energy from regions of higher temperature to the regions of lower temperature. Why does it do so? To bring equilibrium state that is desirable. And what phenomena does it give rise to? This gives rise to the phenomena of thermal conduction. Now, what is happening in diffusion? If the different parts of the gas have different molecular concentrations, then the molecules of the gas will carry mass from regions of higher concentration to those of lower concentrations. Why does it do so? To bring the equilibrium state. What phenomena does it give rise to? This gives rise to the phenomena of diffusion. Now let us concentrate on each phenomena one by one. I take up the case of viscosity first. Let us make some simple assumptions to derive a simple formula for viscosity, to understand why viscosity is coming into play and on what factors does viscosity depend. So this is a simple model on which we are trying to work. Consider an ideal gas flowing in parallel layers between two horizontal planes PQ and LM. The velocity of flow of the gas above an intermediate plane AB is greater than that of the gas below AB. So this figure is showing the three planes of which I have just talked about: AB plane, LM plane and PQ plane. AB is the intermediate plane, PQ is a layer plane which is just above AB, and LM is a plane below AB. The distance between the planes is given by the mean free path equal to lambda. The layer above AB, just let me again briefly tell you, as you can see, the gas molecules moving along the intermediate plane AB are travelling with a velocity v. The gas molecules moving along the plane PQ are travelling with a velocity v plus lambda dv by dz, and the velocity of the molecules along the plane LM is v minus lambda dv by dz. You will understand in a few seconds what is dv by dz and why we have written what we have written. The layer above AB exerts a tangential force on the layer below AB, tending to accelerate it forward, while the layer below AB exerts an equal force on the layer above AB, tending to retard it backwards. So you can see the layer above AB I have just shown you has velocity more than the layer AB, and the layer below AB has a velocity less than the velocity in the layer AB. So both of them are going to exert some kind of tangential force, but because the velocity is more in the layer above AB, that layer is going to exert a force which tends to accelerate it, and because the layer below AB has a lower velocity, this layer tends to retard it backwards. So one force is acting forwards and the other force is acting backwards. Thus these forces tend to reduce the difference in velocities on the two sides of AB. This property of the gas is called its viscosity. Now viscosity, as you all must know, plays the same role as resistance in mechanics. As friction in mechanics, resistance in electricity and magnetism, viscosity in gases. Now let us explain the viscosity from the kinetic theory. The molecules above AB have a greater velocity of flow, as I have just mentioned, and hence they possess a greater average momentum in the direction of flow than those below it. Now, on account of thermal agitation, there is a transfer of molecules of greater average momentum downwards across AB. Thus, the layer of gas above AB suffers a loss in momentum. Why? Because it is giving momentum to the layers below it, whereas the layer below gives rise to a retarding force and a gain in momentum gives rise to an accelerating force. Therefore, the layer above AB experiences a retarding force in the backward direction, while the layer below AB experiences an accelerating force in the forward direction. So now what we have? We have two forces, opposite kind of forces acting in opposite direction. This causes the phenomena of viscosity to originate. Now let us derive the expression for the coefficient of viscosity by a simple mathematical analysis. Let small n be the number of molecules per unit volume of the gas. Now this is very important. Always remember, small n is the number of molecules per unit volume and capital N is the total number of molecules. Let V bar be the average velocity due to the thermal agitation with which they are constantly moving in all directions. Now let us consider the molecules crossing the unit area of the plane AB from the two planes PQ and LM situated at a distance lambda, which is the mean free path of the molecules from AB. On arriving at AB, they will first collide and hence the transfer of momentum occurs. Molecules coming up will give momentum, molecules going above will take momentum. Again I am showing the figure for proper understanding of what is happening. This is a very simplified way of understanding what is viscosity, how does it originate, and how do we get the mathematical expression for viscosity. Let V be the velocity of flow of the gas along the plane AB. Now very important, what is dV by dz? dV by dz is the velocity gradient measure in a direction from PQ to LM perpendicular to AB. Then the velocities of the gas along the planes PQ and LM will be V plus lambda dV by dz and V minus lambda dV by dz. Now again students, you have to understand the significance of the term lambda dV by dz. We have lambda into dV by dz. Lambda has dimensions of length, dV has dimensions of velocity, dz again has dimensions of length. So a length in the numerator will be cut by the length in the denominator and we are left with velocity. So it is very important to multiply dV by dz with lambda to find out the expression for viscosity. Let the number of molecules crossing the unit area of AB per second be 1 by 6 m into n bar. Why 1 by 6? Because we have 3 axes, x, y and z, so 1 by 3, and we are considering only the positive axis. So if we consider both positive and negative axes, then we have 6 axes, and therefore we have to take 1 by 6 m into n bar. N bar is the number of molecules per unit volume, and V bar. Okay, so I will just derive the expression for the viscosity. I hope you've understood up till this point.